Time for a moment of inertia, the resistance to change in angular motion. We do know that torque does equal R cross F, which is, of course, the radius times force times sine theta. Okay, but we also know that torque equals I alpha, the moment of inertia, the resistance to change in angular motion multiplied by alpha. Okay, and alpha is the angular acceleration. Now for Physics 1, we'll be donating all these equations, okay, for you to use, and those will be fine. But the moment of inertia for a point mass has a general equation of just mr squared, and that's when the whole mass, of course, is going around somebody else. Okay, so point mass 1 you should know, the rest, you should be provided. Maybe you should know a disk is 1/2 mr squared, and a sphere is 2/5 mr squared, but they should be providing for you. Now, of course, if we, for my mechanics, if you have a irregularly shaped object, you will be expected to take the integral of that. But just remember the integral I. I is the integral of dm, okay, times r squared, and we've been through this quite a lot. And remember, of course, you'll probably be given a lambda, which is, a function of mass, okay, over a length probably, and then therefore dm, okay, of course, is going to equal, okay, a lambda dl. Now you can call this dx, by the way, or dr, d little r if you'd like. And this one really should be I, okay, is equal to the integral of dm times r squared. Okay, now lambda may or may not be a function, okay, of r. Okay, remember, if it is a function of r, you do need to plug that into the equation. Okay, but if it's not a function of r, you can just leave it as lambda dr, and then you can integrate this equation. And in general, you'll be integrating probably from 0 to L, and you'll be left with something to the third power, but one of your L's will divide out, and you'll have something times L squared. So, but we've been through quite a few examples of those. Okay, so that is our, moment of inertia. Now, from that, we do have an equation for angular momentum that is L, okay, equals I omega. So moment of inertia multiplied by angular velocity. But remember, L is also equal to m r cross v. Okay, so in other words, L equals m, that's an m, times r times v, and of course times sine of theta. Theta, most of the time for us, is going to be 90 degrees. So if I have a ball coming in here and it's going to collide, and let's say it attaches to this rod and they both rotate afterwards, this is a point mass coming in, but we have to remember that L1 does equal L2. Angular momentum initial does equal angular momentum final. Okay, so but for this one, we're going to have to use L equals mv times the radius r. Now remember, sine of 90 is going to be 1 there. Equals. Now we're going to have two things rotating afterwards. Okay, so then this guy here is going to be m r squared plus, okay, now we have a bar rotating on one end. For this one's going to be 1/3 ml squared, okay, plus final angular velocity, or times final angular velocity. So where did I get this magic from? Well, there's a moment of inertia I for this beam here, this rod. If you look at the equation, that's going to be 1/3 ml squared, the length of it. And the ball here, that's a point mass rotating around somebody else. So that's why it's mr squared. So essentially, L1 equals L2. In this case, we're using mvr. And then the second half of this is we're setting equal to I omega. In this case, the I is because of a ball and a rod that's rotating and multiplied by angular velocity omega. So we have to remember that an object traveling in a linear sense, if there's a radius associated with it, we use this equation to get its moment, or to get its angular momentum. Okay, now please remember though that torque, this is our shortcut, does equal delta L over delta T. Okay, just like I talked about, linear momentum divided by the change in momentum over change in time equals force. This is an equation that we've been talking about, quite often, okay, with our angular momentum. Now there's another example that we can use for this. What if a girl is rotating and her arms are out, then she brings them closer into her body? This one will be straight up I1 omega 1 equals I2 omega 2. The thing to remember with both of these examples, that kinetic energy 1, okay, does not equal kinetic energy 2. So these angular momentum examples, okay, your kinetic energy is going to be different. When she brings her arms in closer to her body, she does work and makes herself spin faster. So she's actually spinning faster when, okay, her arms are in. Therefore, we got more kinetic energy rotational than we did initially. So the kinetic energy rotational final in this case would be larger than kinetic energy 1. Okay, now if we go back to this example here, the kinetic energy of this ball coming in, okay, is going to be greater than the total rotational kinetic energy afterwards. So remember that kinetic energy is not conserved with angular momentum conservations, okay, for that reason. Okay, so that's a good review of our dealings, I guess, with moment of inertia and angular momentum.